So I came across this article and I thought, I really don't understand the Java garbage collector. I really have to get to, like, why haven't I, you know, dug deep? Especially because in languages like C, where we have to manage it, we can learn from the Java garbage collector ourselves. Maybe we can transition some of the principles, because the Java engineers are good engineers themselves, and transition some of the principles they have into what we're using. But the thing is, I found this article written by Franz Knopf, and I assume I pronounced that right. But I said, it's great, but it doesn't dive deep enough. We need to get deeper, boys. We need to go further. So I looked again. I saw, this time I knew what I was looking for. I found this one randomly, but then I saw this specifically. I said, that's good. Geeks for Geeks, great source. Great source. But we need to go deeper. Bam. We are going straight to the source, straight to the docs. To just show you how great this website is, my pen tool cannot draw past a certain point, because the website, as you can see, it was orchestrated for perfection. This is what a website should look like. None of this JavaScript nonsense. None of this CSS uselessness. None of that. You can see I already had pre-markings here. It's at about an hour read. We don't have attention span for that. We're actually adding some gameplay footage to the right now as we speak, because we don't have the attention span for that. We can't do that. We are Gen Z developers here. That's not for us. I actually looked into the my viewer age range. We're Gen Z, most of us. So we can't do that. We need gameplay footage to the right. We're not going to read this full thing. We're going to skip over the JVM, the JDK, the JRE. And if none of that makes sense for you, you've already probably skipped off of this video anyway. So we're gonna dive deep. We're gonna go right down here. Bam. Bam. The garbage collection. This is the OG of OG sources. We're gonna first read through that, and then we're gonna compare. Well, we're gonna read these two sections, and then we're gonna compare what was taught in the other two articles. Let's get started. What is automatic garbage collection? Please tell us. We're here to learn. We're here to know. Automatic garbage collection is the process of looking at heap memory. Beautiful. Memory already allocated by the application. Identifying which objects are in use and which are not. Deleting the unused objects. An in-use object or a reference object means that some part of your program still maintains a pointer to that object. An unused object or unreferenced object is no longer referenced by any part of your program, so the memory used by an unreferenced object can be reclaimed. If that didn't make sense to you, all it says is, let's say we have our object here. We're going to just represent it as a circle. If something is pointing to it still in our code during execution, you know what? We'll keep that object around. But if no part of your code that's being executed is using that object, we eliminate it. We should send it to the shadow realm, get rid of that sucker. I used the wrong tool here. We get rid of it. Eliminate that object. Pretty easy. So far so easy. The Java developers are the great documentation. This is excellent documentation. So if nothing is pointing to our object in Java, it is going to be reclaimed. In a programming language like C, allocating and deallocating memory is a manual process. Add Rust to that list. I think Rust has the, well, actually, I think it has some manual intervention. I think one of its features is automatic. Maybe it does have a garbage collector. I think that's a topic I want to dive into later. Trying to learn Rust. In Java, processes of deallocating memory is handled automatically by the garbage collector. The basic process can be described as following. 1. Marking. The first step is in the process called marking. I'm assuming marking the territory. As you can see, color, I'm not saying what it is, but we all know what the color is. We know what it's marking. It's marking its turf. This is where the garbage collector identifies the pieces of memory which pieces of memory are in use and which are not. Okay. I wonder how it, does that. I'm assuming it has like a memory too that has references and then checks, where pointers still are, and it kind of does the deallocation there. Reference objects are shown in blue. Unreferenced objects are shown in gold. Huh. Like a shower? Interesting. All objects are scanned in the marking phase to make this determination. Okay. Interesting. All objects are scanned. Gotcha. So it has a... Well, I'm assuming it checks the heap of objects to see if there are any references pointing to it. I wonder if that's how it's doing it. This can be a very time-consuming process if all object systems must be scanned. Okay. Probably not. See, literally the next line. Normal deletion... So I'm assuming the next processes are the ones that solve for this right here. Step 2, normal deletion. Normal deletion removes unreferenced objects, leaving referenced objects and pointers to freeze. Okay, wait. Will this be answered? Like, what is the architecture solution for not scanning every object? The memory allocator holds references to blocks of free space where new objects can be allocated. Okay, that's fine. That's after post-deletion. The memory allocator creates references to these newly deleted objects wherever they were. Okay, that's fine. Assuming it has, the reference and then the space, most likely. To further improve performance, in addition to deleting unreferenced objects, you can also compact the remaining referenced objects by moving referenced objects together. This makes a new memory allocation much easier and faster. Okay, so just move the heap over. Gotcha. Definitely better than that, but again, not exactly. This doesn't exactly dive into the algorithms themselves, which probably, let's be honest, above our heads, or mine. I actually, you know what? One of you might be a Java developer and know all this stuff, and I actually do want to hear about it. So that'd be great. Why generational garbage collection? As stated earlier, having to mark and compact all the JVM is inefficient. Right. As more and more objects are allocated, the list of objects grows and grows, leading to longer and longer garbage collection times. However, empirical analysis of applications show that most objects are short-lived. This is an example. Okay. Gotcha. The y-axis shows the number of bytes allocated, and x shows the number of bytes allocated over time. Okay. Gotcha. Bytes surviving, but bytes allocated. Quick, this is like the YouTube view counter, honestly. Straight plummet. As you see, fewer and fewer objects remain allocated over time. In fact, most objects have a short lifespan, as shown by the higher value in the left side of the graph. So, survived by, like, it looks like, a quick allocation initially, and then a straight plummet. JVM generations. The information learned from object allocation behavior can be used to enhance performance of the JVM. Therefore, the heap is broken into smaller parts or generations. The heap parts are young generation, old or 10-year generation, and permanent generation. Interesting. Okay, this is starting to make a little bit more sense. The young generation is where new objects are allocated and aged. When the young generation fills up, this causes a minor garbage collection. Okay, so gotcha. It's like broken up in parts. So like whenever young fills, they get axed. Minor collections can be optimized, assuming a high object mortality rate. A young generation full of dead objects is collected very quickly. Some surviving objects are aged and eventually move to older generation. Okay, gotcha. So you can have a object move through generations. So if a young object stays longer, I'm assuming that's how it is. A young object stays too long, it moves over to an older permanent generation. Stop the world event. All minor garbage collections are stop the world events. This means that application threads are stopped until operation completes. Minor garbage collections are always stop the world events. Okay. So whenever a young generation fills up, every time it stops threads. Interesting. Okay. Well, I wonder why you know they're doing like a stop the world event. The old generation is used to store long surviving objects. Typically, a threshold is set for young generation object, and when that age met, the object gets moved to the old generation. Right. So it's like a transition period. Like we thought. We knew. We knew. Maybe we should be Java developers. Maybe we're actually good enough. Eventually, the old generation needs to be collected an event called major garbage collection. Okay? Major garbage collection also stop the world event. Okay. So all threads stopped. Well, I'm assuming they're stopping all threads just because they could be referencing. Well, no, because like you wouldn't, if a thread is referencing it, it would, I guess it would like transition. Maybe the transition is necessary. So when, a young is moved to an old, that can be an issue for the running thread that is referencing it, and then like the memory allocation needs to stop. And then I'm assuming like threads also, you spin up a new thread, or any thread is going to need to like fill this young generation with its data. So maybe it's like a twofold approach of why, all of this is like a world event. Stop the world event. After major collection is much slower because it involves all live objects. So for responsive applications, major garbage collections should be minimized. Also note that that the length of stop the world events for major affected by kind of major garbage collection is affected by the kind of garbage collector that it is used for old generation space. Right. Okay. Makes sense. The type of garbage collector affects how long it takes. Fair enough. The permanent generation contains metadata required by the JVM to describe the classes and methods used in the application. Okay, gotcha. So I'm assuming none of this transitions. So I might be wrong in this diagram. This might be off. Let's do. The permanent class is popular with JVM at runtime based on classes in use by the application. In addition, Java. At this point, I've been reading this so long that I see JVM. Java SE library classes and methods may be stored here. Classes may get collected, unloaded, if the JVM finds they are no longer needed, and space may be needed for further classes, and permanent generation is included in full garbage collection. Okay, interesting. So the clearing out of the permanent is also done by, the major garbage collection. Or is it full garbage collection? Let's see. Was full the same thing as major? Or maybe they're two different things. Maybe the full and then the major garbage collection are actually just two separate entities. Interesting. So I wonder, okay, here we go. This part will actually, dive into how it's done. So luckily we're pretty close to the end. So I know I'm hoping the gameplay footage is sufficing, because it is interesting. This is pretty interesting, especially with the how they decided to just like separate things into like young, old by using this like surviving, byte allocation. Though I do see why, developers in C and where you have to clean up your memory do not like this garbage collection methodology, because this relies on you trusting the algorithm. And I've read posts on different issues, like for example, I was reading through Pinterest where they were allocating, they were using databases. I think it was Cassandra, and the early adaptation of Cassandra had a bad algorithm, or not bad necessarily, but an algorithm that didn't work for their node reallocation, where nodes would get too large, and then the algorithm would not spread it out to other nodes, and then eventually the major node would fill up. So it would be something like we have a node here, node here, node here, node here. All these are database nodes, and the algorithm would try to like spread it out to, or it would like spread it to one. This node would grow too large, and it would not, and then it would not distribute for one. The algorithm wouldn't distribute it down. And then another issue is when it grew too large and you manually distributed it, it would then refill back up. So you would face the same exact issue, which, same thing here. Like, let's say you don't think this algorithm is the best for you, you're gonna be pretty pissed if it like deallocates, bytes, in a way that you're unaware of. Or not bytes, but necessarily, but your memory. So finally, let's learn about like the generations here. I think that is like the major points. Now that you understand why the heap is separating to different generations, it is time to look at how exactly these spaces interact. I love pictures. Again, very Gen Z, very cutesy, very demure. I think I just proved myself as a Gen Zer with the statement there. The older generation might not get what I just said, but I had to establish myself as the Gen Z dev I am. I know some of you are questioning it, but the pictures are very cutesy, very demure. So now that we understand why it's broken up into different generations, right? It's time to look at how exactly these spaces interact. The first picture, the pictures that follow walks through the object allocation aging process in the JVM. Love it. Love a good picture. First, any new objects are allocated to the Eden space. Both survivor spaces start out empty. Okay, that is that one is a pretty good name, I have to admit. So Eden and then survivors. It allocates it first to Eden. Got it. And then when Eden space fills up, a minor garbage collection is triggered. Okay, this is, I'm guessing, the young generation here. So everything is just allocated first to Eden, and then a minor garbage collection is triggered. Reference objects are moved to the first survivor space. Gotcha. So the survivors go in. Unreferenced objects are deleted from Eden. Fair enough. Rapture. Get them out. They were referenced anyway. They weren't needed. At the next minor, what's this called? Garbage collection. I'm assuming that's what GC stands for. Garbage collection. The same thing happens for the Eden space. Unreferenced objects are deleted and referenced objects are moved to survivor space. So yeah, I'm assuming like Eden gets filled up. Like it gets deleted and then filled up. Unreferenced from deleted and referenced objects are moved to the survivor space. However, in this case, they are moved to the second survivor space. In addition, objects from the last minor garbage collections on the first survivor space have their age incremented and get moved to survivor space 1. Once all surviving objects have moved to survivor space 1, both survivor space 0 and Eden are cleared. Nice. So I guess this is kind of XY deployment, huh? XY deployment, but for memory. Let's say I need to clear out survivor space 1. I'll just toss it and then fill it up here. I wonder, maybe because it's like a synchronized thing, I wonder why they don't like clear survivor space 1 and then they clear Eden. I guess it is more efficient to do both at the same time. And what I'm thinking now, spoilers, what I'm thinking is they're gonna once they fill up survivor space 2, it's kind of like once they fill up Survivor Space 2, they're gonna stuff the other stuff into Survivor Space 1 and then move it from Eden to Survivor Space 1, and then again XY deployments out here, switching back, switching forth, the good stuff. Kind of looks like a battle royale if I'm being honest. When I saw Survival Space 1 and Survival Space 2, and Eden's just a great name. I don't know why they say Java has no sense of humor. Java developers have no sense of humor. This is pretty good. Notice how we have differently aged objects in Survivor Space. That's true. That's true. We do have a 1 and a 2 here. That's a good point. At the next minor garbage collection, the same process repeats. However, the time the Survivor Space switch, however, this time the Survivor spaces switch. Reference objects are moved to Survivor Space 0. Predicted. Spoiler alert. I warned you guys, but that is how it happened. Surviving objects are aged. Eden and S1 are cleared. Okay. So the S1 is cleared. So okay. So now ones are become, H2. I wonder when the permanent comes into effect. So far we've had what, 2 transitions and then aged up to 3, this slide demonstrates the promotion. Okay, so I'm assuming this right here will be the final, tenured, aka the old heads, the old generation, the millennial space. Even though I'm teetering, might be teetering there. I might be sent to the retirement home myself. This slide demonstrates promotion. After a minor garbage collection, when aged objects reach a certain age threshold, 8. In this example, they are promoted from young generation to an old generation. As minor garbage collection continues to occur, objects will continue to be promoted to the old generation space. Okay, so makes sense. Okay, 8. So it looks like 9 is the threshold here. Once you hit 9, you're actually, done. You're sent to the retirement home, become a 10x dev, and then sent to middle management for eternity. Beautiful. Okay, so that pretty much covers the entire process of young generation. Eventually, a major garbage collection will be formed on the old generation. So yeah, the old generation is just ignored for the garbage collection. The old generation, which cleans up the compact space, because I you know what? I don't mind the setup. I don't mind the setup. I think we've, I get the get the logic behind it. Okay, in summary, Java divided into 4 spaces. Actually, let me do this. 4 spaces. 1 is Eden. Right here. Then we have our XY deployments right here. Let's use a different color for these. We have XY deployments, even though they're not XY, it's space 0 and space 1. And then we finally have our retirement home right down here. And this is, well, I actually forgot the name of it. The tenured, the retirement home. The tenured. So, let's say you're a piece of memory. Right here. You first get sent to Eden, and you're assigned a value of 1. Let's say you're still referenced. You are sent to the space 0. Actually, I think it's 0. You get assigned a value of 1. Yes. So actually, let's restart this. You start with no value. You're referenced. You're still referenced. So you get sent to space 0. You give it a value of 1. Okay. Bam. Minor garbage collection happens again. Oh, okay. Eden is get cleared out, but you're still referenced, right? All objects are deleted from Eden. Bam. There's a purge. But then there's also a purge and space 0. That's not great because you're still referenced. You're one of a special object. So bam, purge. Oops. Bam, purge. But you escape. They had mercy on you. So you get moved over to S1. Bam. You get reassigned a value. 2. Great. Now you've been the purge once again. Things are getting purged. Instead, it's Eden and S1 being purged off. So everything from Eden gets sent to S0 and assigned a value of 1, and then everything from here is moved over and increased in value. So now, as a memory object, you're going over here and you're increased to 3. And then eventually you're gonna have this like back and forth cycle going here, back here, every time until you hit 9. It seems like that's the magic number. Once you hit 9, you are sent to retirement, finally. You're done suffering in agony, and you get sent down to the tenured lane, sent to retirement, sent to the old whatever space. I can't think of it. I was just reading Java docs. My brain's melted at this point. But now you're sent to the tenured space, and eventually a major purge, and if a major purge occurs, you're gonna be cleared out. But for now, you are still in it, and I think that's the ultimate dream of any heap object. I assume it's just to be tenured. That's the dream. But honestly, a very good Java, doc description. I think this clears it up. Of course, it's not the full detailed Java heap collection, but I think if any of us are going through a Java interview, we're gonna steamroll it.